Out on the Pacific, far to our west, the ocean and atmosphere are constantly in motion, building the systems that eventually reach us here in the Bay Area and cross the United States. High pressure systems, low pressure systems, fog, and thunderstorms, they're all part of the same connected story of weather. In this video, we'll talk about that weather, particularly in the continental United States, including air masses, weather fronts, cyclones and anti-cyclones, and localized extreme weather like thunderstorms and tornadoes. To begin to talk about weather, we need to start with air masses. These are kind of like the air parcels we learned about in the atmosphere module, except they're gigantic and they're not just a teaching tool. They're something we can observe with scientific instruments. Air masses are these large bodies of air more than 1,000 miles across and a few miles deep. These masses are uniform, meaning they don't vary too much throughout the mass in terms of air temperature, humidity, or stability, which is the tendency for air to rise. These masses are recognizable and they move as one unit. So in this satellite photo, we can see an air mass pretty clearly in a high pressure zone over the ocean. Air masses develop by parking themselves over areas with uniform land or sea surfaces, and this allows them to develop those uniform characteristics. Meteorologists or scientists who study weather have identified a number of areas on the Earth's surface that produce air masses pretty consistently. And we call these source regions, and they come in a few flavors, combining their latitude, so polar or tropical, and their continentality, either maritime, meaning over the ocean, or continental, meaning over the land. In North America, we have 6 major source regions. So continental polar over northern Canada, maritime polar over the North Pacific and Atlantic, continental tropical over the deserts in our southwest, and then maritime tropical off the coast of Mexico and in the Caribbean Sea. So these source regions develop the air masses that later move over the United States. We talked a little bit about weather fronts during our module on the atmosphere, so this should look familiar. To refresh, a weather front is a boundary between two unlike air masses. It's a zone of collision between cold and warm air. So we get a cold front when advancing cold air meets warmer air, and you should remember this from the polar front. Cold fronts send warm air up into the atmosphere, causing these tall cumulonimbus clouds, which give a lot of rain, and later we'll talk about how they can cause thunderstorms. A warm front, on the other hand, is when advancing warm air meets colder air, and this causes the warm air to move up more smoothly, like it's going up a ramp. So this creates clouds at differing altitudes, and rain will be more moderate than it is with a cold front. On weather maps, you'll see cold fronts indicated by a line of blue triangles pointing in the direction of the cold air masses movement. Warm fronts are indicated with red half circles pointing in the direction of the warm air masses movement. Oftentimes in the US, warm and cold fronts can form together out of the same boundary between two air masses. The cold air from the north and the warm air from the south press against each other, but neither displaces the other. That's called a stationary front, like the one in the upper left corner of the map here. When an atmospheric disturbance occurs, either in the air currents at the top of the troposphere or from temperature contrasts or surface irregularities, the air masses can start moving, and then the cold and warm fronts develop. So when the fronts curl around, we get a storm system called a mid-latitude cyclone, or a cyclone that forms between the polar region and the tropical region. Mid-latitude cyclones are large, mobile, low-pressure systems caused by the cold and warm air masses circulating and then converging in the center. So these cyclones are responsible for most of the weather changes in the United States. The air in these systems moves counterclockwise in the northern hemisphere and moves inward toward the center. Because there are two fronts, a cyclone will bring both patterns of cloudiness and precipitation. So there will be more gradual cloud formation and moderate precipitation with the warm front, and then a milder zone in between, and then the heavier precipitation with the chance of thunderstorms during the passage of the cold front behind. We also see the exact opposite of the mid-latitude cyclone, which is the mid-latitude anti-cyclone. These are large, mobile, high-pressure zones that also move from west to east. Because they are high-pressure zones, they push air out. So there are no converging air masses here, meaning no fronts, and this produces clear and dry weather. We can see an anti-cyclone here in the picture from the top of the video. The wind will be low near the center, but increases toward the outside, especially at the eastern edge. And on occasion, anticyclones will actually stay in place and can even block cyclones from moving for several days. So when this happens, the weather may be nice and dry under the anticyclone, but the region back to the west will be getting a ton of precipitation from the cyclone. A lot of weather here in the Bay Area, including our fog, is actually thanks to an anticyclone. So this is a diagram of the Pacific High, which is a semi-permanent anticyclone that hangs out over the North Pacific. It's formed by sinking cool air from the Hadley cell, and it moves around depending on the season, going a bit north in the summer and south in the winter, though it's always north of the tropics. The Pacific High is connected to us here in the Bay Area because it sends wind out toward our coastline. The wind curves like this due to the rotation of the Earth, also known as the Coriolis effect. Because the wind curves when it comes off of the Pacific High, it moves south along our coast, dragging the surface water along with it. So the surface water is then replaced by colder water from below the surface in a process known as upwelling. This is why the ocean water at our beaches here in Northern California is so cold, even in the summer, because it comes up from below the surface. And this also causes our fog. Air that's been warming out over the Pacific, collecting moisture from the surface, is brought in by the sea breeze. And when that moist air passes over the now cold surface of our coastal waters, it starts to cool down too. And this brings it to the dew point, causing the condensation that we know as fog. So we've focused mostly on mid-latitude weather, but before moving on, let's look at tropical cyclones. So these storms have different names depending on the location. There are hurricanes in North and Central America, and then typhoons in the western North Pacific, and cyclones elsewhere. So they're smaller than mid-latitude cyclones, but they're usually more intense in wind and damage. Unlike mid-latitude cyclones, hurricanes aren't formed by fronts. They're fueled by warm, moist tropical air. As that air rises, it cools and condenses, releasing heat. That extra heat makes the air rise even faster, pulling in more air and speeding up the winds. But once the storm moves over land, it loses that moisture supply. So it can still cause major damage, but it weakens quickly. By contrast, let's now turn to smaller, localized storms that can still bring extreme weather. Thunderstorms are local, short-lived storms with lightning and thunder associated with dense, towering cumulonimbus clouds. These develop from warm, moist air like that from maritime tropical air masses, and they need a lifting mechanism. So either convection or frontal lifting, or even just moving up a mountain slope. The basic process is familiar. Warm air rises, cools, and condenses. But here's the twist. Inside these clouds, the rapid updrafts and downdrafts toss droplets and ice crystals around, which collide and transfer an electric charge. Ice crystals become positively charged and gather near the top, while heavier pellets pick up negative charges near the bottom. So this separation builds up until a discharge leaps from the cloud to the ground. We see this as lightning, and then we hear it as thunder. Finally, the downdrafts take over, the rainfall tapers off, and then the turbulent air calms down. And that's when the thunderstorm dissipates. Unlike thunderstorms, tornadoes are extremely rare here in the Bay Area. They need flat terrain and larger storms than the ones we get locally. A tornado is a small, intense, low-pressure cell wrapped in a violently spinning column of air. They're usually less than a quarter mile wide and become visible when water vapor is pulled into the funnel. They form when wind shear develops. This means upper air that's moving faster than lower air. And this creates a horizontal spin near the ground. An updraft, like the kind from a thunderstorm, can then tilt that spin vertically, and the storm itself begins rotating. That's called a mesocyclone. In about half of all mesocyclones, a tornado will drop from the cloud, touch down on the ground, and then produce really destructive winds. And these storms are compact and powerful, but again, they don't usually happen here in the Bay Area. So now that we've covered a few types of weather and their causes, in addition to precipitation and clouds from past videos, we can start to take better notice of these phenomena. So for our 5th selfie field trip, you will be posting a picture of a weather event. It can be something spectacular or something ordinary, but share your pics, answer the questions, and then reply to 2 or more peers. In our next video, we'll start off Module 5, where we'll be talking about climate. Thanks for watching, and I will see you next time.